Dynamics of uniform circular motion. This is where we talk about the forces involved in our uniform circular motion. So we know that to be in motion, in uniform motion around the circle, you have an object has some acceleration toward the center of the circle. And this is called centripetal acceleration. And that's what keeps you in motion as you go around the circle at some constant velocity. And from Newton's second law, we know that to have any acceleration, if you have some mass, you need a force. So you're an object with mass, you're accelerating, and you need a force. So that's where the kind of general equation for the force that pushes you around this circle is mass times acceleration, which we said earlier, centripetal acceleration is v squared over r. Or also, centripetal acceleration is 4 pi squared r, squared r over t squared. So you can use either part of that equation depending on what kind of problem you're trying to solve, whichever one serves you the best. But that's the force that's keeping you in accelerating around a circle in uniform circular motion. All right, so that will help you solve problems like this. An energetic father places his 20-kilogram child in a 5-kilogram cart to which a 2-meter long rope is attached. He then holds the rope and spins the child around in a circle, keeping the rope parallel to the ground. If the tension on the rope is 100 newtons, how much time does it take for the cart to make one rotation? Okay, so diagram. This will be a fun one to draw. Guy spinning his kid in circle. Okay, so guy, he has a rope and a kid at the end of the rope in a cart. And they're spinning around in a circle. What else can we label? We have, this would be the radius, so between the guy and the kid, that length of rope is the radius. The mass of the kid, or the mass of the whole object, I guess we have to consider, is 20 kilograms plus 5 kilograms, so it's 25 kilograms. And, oh, we know the tension on the rope too, so the tension, T, big T on the rope is 100 newtons. That's the force keeping this kid in circular motion. So, it's asking us how much time it takes for the cart to go around the circle. What we can also do is draw a free body diagram for the object. The object has some normal force and weight, always. Since the object isn't accelerating vertically up or down, we know that these two forces cancel each other out, and then the other force in this equation is the force of tension, and that's what's supplying the net force in the direction of the center of the circle. So that's what's supplying that net force, is the tension. Okay, so we know that. We know we have some equation where we have F net equals MA, and now we know that the F net is tension. So we have F net equals tension and is equal to mv squared over r, mass times acceleration. All right, good. What else? So we know from this problem, we know tension, we know the mass of our object, we know our radius, so all we have to do is some algebra and solve for v. So we, to solve for v in this case, we have v equals the square root of the tension times the radius over the mass. So we have our newtons times our 2 meter, 2.0 meter long rope over 25 kilograms. And that is equal to, the velocity is equal to 2.83 meters per second, which will be helpful when we figure out how much time it takes to go around. So we know how fast we're going, and now we can use that to figure out the period, which is how much time it takes to go around the circle once. This is a good example of where we have two different t's. We have a t for tension here, and then a different t for period, which is unfortunate, but just something we have to pay attention to. So here's our equation for period, 2 pi r over v. And we have a lot of this information. We have pi. We have r is 2 meters. And we have our velocity now, 2.83. And so our period, the time it takes to go around the circle once, is 4.4 seconds. So that is a good example of where you use what you know about force, you use a free body diagram and Newton's second law to find out some other parameters of a problem. The speed, the time it takes to go around, maybe the acceleration, something like that.